It's an exciting time. We're glad to have you here this morning, glad to see you here today. And I want to invite Gretchen Miller, if she would please come on out to introduce, or come up to introduce. Gretchen is an associate professor of geology here with a master's degree in earth and planetary sciences from Washington University in St. Louis, and a Bachelor of Arts degree in Geological Sciences from the State University of New York, or SUNY, better known, at Buffalo. Through a grant funded by the National Science Foundation, she and Adrian Leinbach have guided the overall administration of the project, which has involved a collaboration between Wake Tech and the North Carolina State University geology faculty to provide research opportunities to students who are interested in geosciences careers and who want to transfer to NC State or other universities. Are any of the students who got to present their projects to him, are you still with us? Oh, raise your hand. Stand up. Let's give them a round of applause. They got to meet with him this morning in a small group to tell him about their research project. So he was very excited. I asked him about the quality. He said it was outstanding. So let me ask you to welcome Gretchen Miller and let her introduce our guest speaker. Gretchen?
Thank you, Dr. Scott, and hello to everyone. Before we begin, we have a few housekeeping issues to go over. First of all, please silence your cell phones and refrain from taking pictures or videos during Dr. Schmitt's presentation. Second, bathrooms are located in the hallway directly behind the conference center. Take a left, first hallway on the left, and bathrooms are on the right. Dr. Schmitt does not sign autographs, but he does sign copies of his book, which are available for purchase in the pre-conference area where you came in. After the talk is over, there'll be a short break, and then the book signing will begin. And finally, Adrian Leinbach and I would like to thank all of the people who made this event possible. There are a whole lot of folks that brought this together. Please refer to the back of your program for a complete list of those who helped us make this happen. Now I'd like to introduce our speaker. Senator Harrison Hagen Schmitt was born in Santa Rita, New Mexico. He grew up in Silver City and received a BS from Caltech and a Harvard PhD in geology. He earned jet pilot wings in 1965 and helicopter wings in 1967. Selected by NASA as a scientist astronaut in 1965, Schmitt flew in space as lunar module pilot for Apollo 17. He landed in the valley of Taurus Littrow, December 11, 1972, as the only scientist and last of 12 men to stand on the moon. Elected to the U.S. Senate in 1976, Schmitt more recently chaired the NASA Advisory Council from 2005 to 2008. He served as lead director for Orbital Sciences Corporation prior to this year's merger of that company with the aerospace and defense company ATK. Schmitt now chairs the Governance Committee as a member of the Orbital ATK Board of Directors. Please help me in welcoming Dr. Harrison Schmitt.
Thank you. Thank you very much. How many of you are lunar scientists? How many would like to be? Yeah, we got a few. You have to promise me that if I use a term or a concept that you need a more explanation on, that you'll raise your hand or yell or scream or something like that. Because I'm going to, for this particular presentation, I'm going to try to spend some time talking to you about what we have learned about the moon and how it relates to the Earth. The first slide, though, may take a moment to Poor Uncle Rick. Let's quickly review the Apollo space program, since that happened before many of your times. It was a remarkable period, and the landing on the moon, of course, was first proposed by, officially proposed by President Kennedy. Many people had talked about it before in science fiction as well as more practical ways. It was a geopolitical program. It was to counter the Russian, then Soviet advances in human spaceflight, a very critical time for this country and for the world in the middle of the Cold War. As you hopefully all know, John Glenn orbited the Earth fairly soon in the 60s. Apollo 8 then orbited the moon in December of 1968 and effectively ended the space race. Actually, the moon race. Actually, Russian emigres of that time, soon after, indicated that when we first successfully launched the Saturn V, which is in the background of this picture, on a test flight, that it was basically assumed that the race was over. They had not been able to build a rocket and successfully launch a rocket sufficient size to reach the moon. Neil Armstrong successfully landed on the moon in July of 1969. That from the historical point of view brought into that race to the moon. There were 5 additional Apollo missions, that landed on the moon between November of 1969 and December of 1972. Actually, there was a period between November 1968 and November 1969 when a Saturn V rocket was launched every 2 months. And I have to say here that that was because of young people, your age, most of your ages. Apollo was a young person's program. There were some managers that might have been 30 years old or possibly even 40, but for the most part, the average age of the Apollo people was about 25, 26 years. Just have to remember that. That's when you start to really accomplish things. Apollo 13, about which I hope you've seen the movie, which is a good movie, considering that they compressed all of that activity into an hour and 20 minutes or something like that. Apollo 13 was damaged by an explosion and rescued in April 1970. The 3 Apollo missions, last Apollo missions, each or all of them went to different areas on the moon, and the last 3 spent 3 full days there. Exploring, and the training of the astronauts had been oriented towards exploration rather than through test flight preparation. 850 pounds of moon rocks and soil were brought back to Earth. Studies of these samples continues very, very actively today. In fact, team that I'm responsible for is preparing a paper today, or right now, that integrates the results of those samples into other information, remotely sensed information that's been gathered since Apollo. Great new understanding of the Earth, particularly its early history, has come from understanding the history of the moon. And the bottom line, I'll give you to that right now, the first 800 to a million years of Earth history was extraordinarily violent. We know that now from the moon. That was something we did not know. We didn't even have an inkling about, because the early estimates of the age of the surface of the moon were all much, much younger than that. And having found that out, suddenly you have to have new thoughts about of what was going on the Earth in those early years, a period of time in which we feel very strongly now that the complex molecular origins of life were forming. So that it was happening in an extraordinarily violent period, and we'll talk more about that in a moment. The object of our affection today is the moon. This picture actually is taken from lunar orbit. We were on our way back to Earth when I took this picture, and so on the right third of that picture, as you view it, is the far side of the moon, something you normally don't get to see unless you've been doing some things that you shouldn't. The Apollo 17 landing site is right up there at the edge of this particular image, and compared to where Apollo 11 landed to the south, about 600 kilometers to the south, you see that in this picture. Now, as you are aware, the Earth has, let's say, three major features on it. It has the continents, the continental plates as they're now called, the oceanic plates, and the oceans. The moon has three major features. It has the lunar highlands, the light portions of the moon, which is the oldest terrain on the moon. It has these big basins that you see formed by large impacts prior to about 3.7 billion years ago. And then most of those basins have been filled by volcanic lava, namely what we call basalt, rich in iron magnesium silicates. The Apollo 11 and Apollo 17 both landed on surfaces that were originally covered by that basalt. We'd had a great deal of training in a variety of spacecraft operations. About 3/4 of the time was spent in that training, most of it in simulators, computer-driven simulators. But a week of every month was used for actual field training, primarily oriented towards teaching pilots a little bit about how to observe rocks. They're good observers of aircraft systems, but they had not had much experience observing rocks. And here you see Gene Cernan and myself with all of our equipment except the suits on out in the field area this is probably Nevada. We had a different field site. We worked on real problems. It was a training program that I suggested to Al Shepard, our boss at the time, that we undertake for the advanced missions, and it turned out to be very, very successful. The field vehicle we used to get to the moon is the Saturn V, a really remarkable accomplishment by NASA and the engineers primarily at Huntsville, Alabama, and in the Boeing company and the General Motors company. The Saturn V at this point weighed about 6.8 million pounds. The 5 engines in the first stage was developing about 7.5 million pounds of thrust. And of course, that was sufficient to get us started, moving very, very slowly at this point. After 3.5 days, we were at the moon. We activated the lunar module Challenger that you see here, our real field vehicle is for landing on the moon. And then we were preparing just before, on the orbit prior to landing, getting some navigational sightings from the other spacecraft. And if I can figure out how to operate this laser, that's the other spacecraft for those of you who can look at right in the middle of the picture. The command and service module with Ron Evans all alone in it at this point. And he was taking actual sextant sightings, navigational sightings on small craters in the valley, the position of which had been determined using previous photography relative to the center of mass of the moon. Of course, mass is critical in space. You pay all attention to mass rather than weight. So we were determining our orbit relative to the center of mass of the moon. And that information was then transmitted directly into our computer after being processed down on Earth, so that we had knowledge then in the lunar module, the Challenger. We had the same knowledge that he had about the orbit. And that enabled us to land with great precision down in a very narrow valley, such as you see here. The widest point of the narrowest point of that valley is about 7 kilometers. So it's deeper than the Grand Canyon. The mountains on either side go to 2,100 meters. So you can see that we were trying to get into a very, very precise, relatively precise place. And we landed within about 100 meters of where we had hoped to land, close enough for everything that we wanted to do. The features you'll hear me mention several times, the South Massif, that mountain there in the center, the North Massif on the right, the sculptured hills, just remember that phrase, we'll talk a little bit about it in a few moments. And then just for the geomorphologists in the crowd, I met one this morning, we have an avalanche deposit that has become increasingly interesting because it actually turns out to be 2 deposits. And we'll talk about that more. First view I had out of the right-hand window of the lunar module, you see here the bottom of the North Massif there is about 5 kilometers away. The very typical surface of the moon, what we call a mare surface, that debris layer that you see there averages about 9 meters deep in this valley. It was about 6 meters deep where Neil Armstrong landed, and that varies with the age of the original age of the surface and any other material that might be thrown into that surface and mixed with it. This regolith, as we call that debris layer, is formed by the impact of meteors of a variety of sizes, of course, and it's gradually gardened to those depths. That surface there was originally formed about 3.7 billion years ago, so the 9 meters represents what accumulated and what was developed in that period of time. The object in the foreground is one of our small, what we call attitude control thrusters, a small rocket, about 50 pounds thrust. We'll talk about some of the other details this afternoon if you have a chance to come back. The camp that we set up on the moon, every field geologist has to have a camp, and this is it. It was good for 3 days on our mission. Actually, it had the capability from a consumables point of view to stay for 4 or 5 days, but we sacrificed some of that stay time for payload. And so the scientific equipment that we had, including the lunar rover that you'll see here in a moment, took up some of the payload that otherwise could have been consumable. So as a field geologist, I would have been happy to stay 5 days and just wander around and without any equipment whatsoever, but that was not acceptable, of course, to the physicists and astronomers and others that had experiments. They wanted to get to the moon, and I understand that. Now here's everything that you need to work on the moon. You need a human being, of course. And I don't know whether you can see it or not, but reflected in my visor is the other human being who took the picture. So you got 2 people there on the moon. You've got the camp, and you've got the lunar rover, the Jeep, if you will, the dune buggy that we used, worked extremely well. We put about 35 kilometers total distance on that. And then, of course, the flag of the United States, which made it all possible through its taxpayers. And I thank you very much. Or thank your parents very much. Or maybe it was your grandparents. I'd lost track. Now, we're going to start our geological work here with stratigraphic sampling. Hopefully all of you understand the concept of stratigraphy, something that came out of Nicholas Steno's thinking in Italy, a priest that wandered around the Italian Alps and suddenly realized that young things tended to be on top of old things. And that was in the 1500s, that was the origin of the concept of stratigraphy. And we practiced that on the moon, believe it or not, better than we knew at the time, because these are layered massifs, layered by ejecta from big basins primarily. that was ejecta put there when asteroids hit the moon and formed those circular basins we saw earlier. Now, the way we sample those without having to climb the mountain, which would have taken a lot of time and energy and might not have even been possible, although the rover was capable of going up at least 20-degree slopes and probably better than that, the way we sample it was through boulder that roll down the mountain. And because of the deep regolith, they leave boulder tracks. And this is one of those boulders that we worked on, the biggest one. We actually had seen this on pre-mission photographs, even though those photographs were not very high resolution. This is a 20-degree slope that I'm working on there. And behind that, there's where the lunar module was, over there near the, here, let me go back. It's about 5 kilometers away at this point. And here I think you can see that track that boulder left as it came to rest. My footprints are going down into it and then up the other side. Those footprints, by the way, will stay recognizable for 1 or 2 million years. So again, if you want to leave your footprints in the sands of time, the moon's not a bad place to. Certainly better than Washington, I'll guarantee you that. The only thing that's going to disturb those footprints, for the most part, absent a rare or large impact, is what we call micrometeorites that are gardening the surface and very, very slowly and create what we call space weathering as well as gardening. Now, if you look carefully, you can start to see, with the help of those arrows, I hope, some of the boulder tracks. There are a lot of them on the North Massif. It turns out they're not as prevalent on the South Massif, and we'll talk about why in a few moments. Now, the 2 arrows down at the bottom are the 2 boulders that we had time to sample, Station 6 and Station 7. If you follow their tracks up, their sources are separated by about 500 meters, which was a nice stratigraphic separation. It turns out, we think, very, very fortuitous. And now we're getting closer. These, by the way, these are pictures taken, high-resolution shots taken by the Lunar Reconnaissance Orbiter, which is still in orbit around the moon. It's been there for several years and giving us a lot of new high-resolution information to work with in trying to understand some things we didn't have time to really work on while we were there. So Station 6 and 7, and also if you look very carefully, you can count at least 10 of those boulder tracks. So when some of you go back to the moon and need to do stratigraphy of a massif, you got lots of material to work with, okay? You don't have to measure section, if anybody remembers what that's all about, measuring section. That's something that we used to do, and I don't think anybody does anymore. Also, you have to, because this mountain is high, there's another 700 meters of ejecta above this point, and it's probably ejecta from the basin, the edge of which we had landed near. That is still an active area of discussion, believe me. Now, this is the boulder at Station 6, the big one that you've already seen from the other side. It actually has a contact zone in it between what we call a melt breccia on the left and another melt breccia on the right. But the one on the left is highly vesicular, that is, it's full of holes, which meant it came in, it had gas in it. We don't know what that gas was. I suspect it was a mixture of hydrogen and carbon monoxide. But nevertheless, it did have, and you can see, I think, distinguish the large holes that are in it. And it was hot enough to actually metamorphose, to change, to partially melt even the contact zone, about a meter-wide contact zone. And you could see this in the field. I could see it, got up close and personal, as close as I could get with a helmet on. Now, we have, others have dated the material. We're getting new dates now, again, because of the advancement of technology. is enabling us to use lasers and mass spectrometry to get very, very small parts of these. These rocks are extremely heterogeneous, and you have to get down to actually trying to measure what was melted and get what we call an argon date on what was melted. It takes now this very sophisticated UV laser work. And we have now a general impression that both the breccias here in this boulder are about the same age. They probably the result of the same impact event. They just came at different times. And the mechanics, the hydrodynamics of these large impacts are really not well understood. But clearly a lot of material gets melted, and it moves at different rates and at different times away from the impact point. But 3.9, approximately 3.91 billion years for both of these breccias. It looks like they were related to the same impact, and it was probably the Crisium Basin. Now, I should have pointed out the Crisium Basin in that original slide, but it was the darkest circle over on the right, if you remember the picture of the moon. And it has been neglected a bit in our work on lunar. We tend to focus on the Imbrium Basin and others, but Crisium almost certainly, since it's the same distance from this landing site as Imbrium, it probably did contribute a great deal of early ejecta to the stratigraphy. Now this is the second boulder, Station 7 boulder, which when we worked on it, we didn't know it had a boulder track. We couldn't see it. It was too subtle. It came down earlier. It had been, that track had been obscured by these micrometeorites. And so it wasn't until we got the Lunar Reconnaissance Orbiter pictures that I realized that we had a track that we could trace back up. And so we actually had done what we knew we could do, but had not realized had accomplished. We had at least sampled 2 parts of the North Massif. And it also has a contact between a vesicular, that is a molten melt breccia, and a blue-gray breccia. And that blue-gray breccia, it looks like it's about the same age as the bigger boulder from Station 6, whereas the melt breccia here appears to be much significantly younger. Now there's some big error bars still on these ages, but this one is starting to look like it actually is melt from Serenitatis, whereas the other melt breccias appear to be from Crisium. Stay tuned for that, but right now that looks like where we're headed. This gives you a graphical view of some of the samples we took on those 2 boulders. You can see the error bars are quite large, but there's starting to be a separation, and so I'm fairly convinced that the hypothesis is going to turn out to be correct, that we have both Serenitatis and Crisium samples from that area. This is not universally agreed to yet by my colleagues, but I think we're getting there. Now, the sculptured hills, I mentioned that earlier. These were an enigmatic physiographic feature. You can see there in the box knobs that are very different than this, give a very different impression than what you see geomorphologically than you see for the massifs. This is a view, an oblique view, taken by the Lunar Reconnaissance Orbiter, and I just want to see that the sculptured hills appears to wrap around a portion of the North Massif. And this material almost certainly is material that's come from the Imbrium Basin, the youngest of the large basins on the moon that could have a reach of ejecta this far. So that Lunar Reconnaissance Orbiter has given us that information. That's new information. We didn't really realize that that the sculptured hills material physiographic feature wrapped around like that. And actually now, from other data, that knob is probably related, as is this one, and some others, kapukas that stick through the basalts. That's a Hawaiian term. I just thought I'd throw that out for something that sticks through basalt. The sculptured hills, back to the previous picture, has some trends in it. There's swales that if you start to map them out, you can convince yourself that there are a variety of directions in those, at least two major directions, more or less east-west and north-south. We actually sampled a boulder from the sculptured hills. We weren't quite sure here at Station 8. After we worked on the big boulders over here, we came over and there was just no boulders. It was a very different feature. There were no tracks, no boulders, except for this one. It turned out to be a norite. And there's evidence of that. Maybe there's a gabbroic anthracite right here in what's called the paint splatter feature. It's actually a granular debris flows coming off of one of the knobs. And with another satellite that flew, another instrument that flew on the Indian satellite of some almost 10 years ago now, I guess. It took some images and gathered spectroscopic data that indicate that the sculptured hills have a large number of mafic and ultramafic rocks in them. There's more to be done with this. This work is not complete, but more and more it appears that the sculptured hills are a very large igneous body that it was excavated by the Imbrium event, this 1,000-kilometer basin, and actually thrown into this valley more or less intact, broken but intact. These particular rocks are part of what are called the magnesium suite of lunar rocks that are usually very rich in magnesium, although there are anorthosites associated with them, and appear to be something that was intruded into the lower crust early in lunar history. Probably, you saw that date of 4.35 billion years, probably around that point, because of an extremely large impact called Procellarum. Procellarum is a basin that's about 3,200 kilometers in diameter. It's continental in scale. Again, I draw you back to the Earth. Think about impacts of that scale on the Earth 4.5 billion years ago. It almost certainly was happening. The moon records what was going on in the inner solar system, and that was happening here. And may have been the beginning, the seeds of the continents, the early continents, because you get these very thick melt sheets formed, particularly in an aqueous environment like the Earth. Water will enhances the melting of planetary rocks. And those melt sheets probably differentiated, that is, that they cooled slowly enough that you got a concentration of various elements at different times to get different kinds of rocks, but mainly you ended up with what we call a felsic or silicate-rich continental seed. There is now one piece of evidence that indeed happened here on Earth, and it's in zircons. The technology, again, has gotten to the point where you can date when these little crystals formed. And the interior of those crystals, zircon crystals, particularly the ones we find in Australia, the oldest now is 4.4 billion years, which is about what you would have expected had one of those big impacts occurred on Earth. So we're gradually tying these things together. So that's just to illustrate that. Now that's that boulder, and as I said, norite boulder. Getting a better and better date on it now of about that. And this date is starting to show up, and the more precise work show up in a lot of the MG suite rocks. So we think that some major event occurred on the moon, and my guess is it was this Procolarum Basin formation at about that time. The possible ages of the various basins, there's Procolarum now outlined. You'll have to take my word that that outlines a basin, but it is the thinnest. We've had a gravity satellite, measuring satellite around the moon in recent years, and it is the thinnest part of the crust. And so that's another evidence that it is indeed a large basin. Indeed, in some places you can actually define the rim. The South Pole Aitken is another one of these large basins. That's a guess at its age. The South Pole Aitken is 2,500 kilometers in diameter, another continental scale basin, but it's mostly on the far side of the moon. Some of the basins that are important because they do not have what we call mass concentrations in them. They formed when the crust was still could adjust what we call isostatically. That is, it would compensate for any gravitational anomalies that might exist. But on the other hand, after that, we started to get basins that could not adjust. So there was some strengthening event within the crust that occurred around 4 billion years ago. And then Imbrium, which we talked about earlier. Again, just to remind you, Apollo 17 landed right there. Apollo 11 landed right down here. Right down here. Apollo, 16 was right here, Apollo 15 there, Apollo 12 over here, and Apollo 14 right over here. So we haven't really explored much of the moon. I mean, the area is relatively small, so there's a lot left to be done, and everything I say is based on that limited exploration, plus the remote sensing work that's gone on since. The basalts, I don't want to leave them out. They are an important part of lunar history, and actually volume-wise they're not that big, but they certainly do create the man in the moon and the rabbit in the moon and person in the moon, whatever you choose to call it. We have a lot of age measurements. They're really quite a spread from 3.5 to 3.8. There's something going on in the isotopic systems in these basalts that I don't think we understand at all. If you take an average of the basalts just in the Valley of Taurus Littrow, it's coming out to be about 3.74. But I don't like averages. I want to understand why there's that big spread, and it's independent of isotopic systems. It's in rubidium, strontium, in the argon systems, every lead systems. So we don't understand that yet, but hopefully I think we will. Prolonged cooling, radioisotope migration, impact resets, all of these may be playing a part in giving us this strange spread of ages for the basalts. Now, one of the things I did at this same station, Station 1, was to take a rake sample. We had developed this, it's actually a sieve. We wanted to get a large number of small fragments. We had previously realized that in the population of small fragments, you got more exotic fragments that had been thrown in by other impacts. And so this was one place where we did it. Well, it turns out that we didn't get any exotic fragments in this sample. We got all basalt fragments. And it shows, though, it was great because there's a lot of data on those fragments. Some 59 samples fit into what we, again, call a differentiation sequence of crystallization, of fractional crystallization of these basalts. And it turns out olivine almost certainly was the first mineral to come out, anorthite the second, ilmenite, and clinopyroxene finally. And there are only a couple small groups of samples in this 59 that appear to fall outside this differentiation sequence, but they're they're different chemically. One's very high in titanium, one's very low in titanium. Just to give you some graphical things to look at here, that's the differentiation sequence. One of the interesting things that comes out of this analysis is that, and by the way, I'm using the percent olivine in the rocks as a measure of the degree of crystallization. I didn't have any other thing to use, but it does give you some consistent information. And one thing it says is soon after olivines came out, plagioclase started to crystallize, and it probably floated because it would be less dense than the magma, than the lava. So it probably floated, and therefore you got fractional differentiation that way by the floating of plagioclase. We normally don't think about those kind of things happening, but floating apparently was very important. And then ilmenite, the titanium iron mineral started to come out, and the titanium ratio became more constant. So again, these graphs just show you some of the things that come out of that. Now, Shorty Crater turned out to be, it was planned to go to Shorty Crater. It was a dark crater. The ejecta was dark around it. It had penetrated that avalanche that I'm going to talk about here in a few moments into the basalts underneath. And we were not absolutely sure it was an impact crater. It sort of looked like one on the low resolution photography, but we thought it might be a volcanic crater. And so if it were, it was worth visiting. Station 4 is shown here, and it turns out that this is where we found the orange soil. And if you look carefully, you'll see some orange there. That's where the sampling was done. There's another spot over here. Some dark soil. There's black ash associated with it. And that's a fairly good picture of the deposit of orange material that turned out to be, when it was examined in the laboratory, extremely fine-grained ash, volcanic ash. Small spheres, less than the average size is 40 microns, extremely small. That's why we didn't see it visually. And you just have to imagine if you get a volatile rich eruption at the surface of the moon, and this ash is volatile rich, then it's in a vacuum of space. It's going to atomize, essentially. It's going to break into extremely small droplets and form these small spheres. Now, here again, we were able to do some stratigraphy. If you put everything together that we know about this, I'm not going to go into the details. There was some kind of basaltic floor when this regolith developed on that floor. Another type of basalt, I won't go into why it's distinguished chemically, was extruded. There was a regolith developed on there, and then this black pyroclastic ash came in. And actually, by measuring exposure ages, solar wind exposure ages, we know now in the core we took, there were, through this, a 70 centimeter core, there were at least 4 eruptions of black ash. So, and they're separated by tens of millions of years. So this is something going on for a fairly long period of time. It's almost like a hot spot that we think about here on Earth, such as Yellowstone and Hawaii and Iceland. That is fairly new information. Nobody had gotten around to really comparing the exposure ages that had been measured in the black ash by others decades ago. But when you put them all together, you see that they make a good sequence of eruptions. And then the orange pyroclastic ash was the last thing that happened. It got most of the publicity, but it was volumerically a relatively minor event. Now, remember that these ash particles have a lot of adhered volatiles to their surfaces, volatile elements, chlorine, fluorine, tellurium, zinc, all those things that we geologists call volatile. And most recently, a team at Brown University has been able to penetrate into these, found little tiny olivine phenocrysts, little crystals in the glass, and the olivine in turn encloses water, indigenous lunar water. And in fact, that indigenous lunar water may actually be the source of, one of the sources of the water ice that we now find at the poles, in that it's migrated to the poles and been precipitated in permanent shadowed areas. Cometary water is another choice for that. And there are reactions, solar wind, hydrogen, and silicate oxygen tend to react and form hydroxyl, and some of that may actually have migrated to the poles as well. So water ice at the poles has a number of different explanations. Oh, and by the way, the reason we found this orange cell, by the way, it's 3.5 billion years old. By all rights, it should have been incorporated in the regolith. But we found it in pristine form. So it had to be protected during that period of time, and so there had to be another lava flow on top of it. And that, even though we may have sampled pieces of that lava flow here, but you just, by logic, it had to be there. And this is something we see on Earth. When pyroclastic eruptions, when volatile rich eruptions occur, one of the last things that happens is a volatile depleted extrusion of lava. You see that in the Flagstaff field and other places. So that almost certainly happened on the moon as well. And then this light mantle avalanche unit that I keep hinting we're going to talk about. But before we do, this is sort of a structural reconstruction of what I think we had in the orange soil deposit, orange and black soil deposit. When Shorty formed by impact, it compressed these layers into and slightly overturned them into this folded area you see. And our core penetrated the orange into the black and then possibly into one of the overturned limbs, and that was that last date that I gave you, the 57 million years. We got all this data in half an hour. It was probably the most efficient work that we did during the Apollo mission. Okay, I've talked about an avalanche. So indeed, something triggered an avalanche off the side of the South Massif. This is the South Massif. This is that light mantle deposit. Well, because of the Lunar Reconnaissance Orbiter photographs suddenly clearly revealed, and they would go back and say, well, yeah, that's there, but we hadn't noticed it. There's an older avalanche underneath, and it's covered by this newer one. And in fact, this part, I may show you something here in a moment, this part of the avalanche is thicker than this part. So it looks like that original, the older avalanche probably was about like that size. Now, unfortunately, before we realized this, just in the last few months, this avalanche, the exposure age on this avalanche had been used to date the crater Tycho. You can follow a ray of ejecta from Tycho up across the valley of Taurus Littrow, and craters up here on the South Massif had been interpreted as being secondary craters of debris from Tycho. Well, it would take an extraordinary set of coincidences, I think, to have two avalanches separated by maybe 100 million years of time, and have one of them related to Tycho. So now I'm suggesting that we start to think about this being triggered by something else, and not by Tycho. So that, unfortunately, we don't like to lose any crater date on the moon, because we try to use crater counting to date surfaces on the moon, and we hate to lose one. But I think we've lost one here. But it gets more interesting. Just to give you a little feeling for what that avalanche looks like. And this scarp that I've got the arrows there on is what we call the Lee Lincoln Scarp. It's a thrust fault scarp, and we'll get more into that here in a second. We actually sampled rocks here at Station 2, but because of the avalanche, we didn't have any boulder tracks. The avalanche had destroyed all the old boulder tracks, which says it was fairly young avalanche, and now just, I won't tease you, but probably about 75 million years ago is when that occurred. And these are just some graben faults, pull-away faults that probably relate to the avalanche movement, the last movement of the avalanche. These are, you can estimate depths, minimum depths anyway, of the avalanche by looking at the impact craters. Again, these last few pictures are lunar reconnaissance orbiter pictures at high resolution. And over here, it looks like it's about 5 meters thick, a little over 5 meters, and down here it looks like maybe 10 to 15 meters. And again, that may be the older avalanche underneath here. Now, this thrust fault, the Lee Lincoln Scarp thrust fault, is of some interest because it may have been the trigger of the avalanche. And indeed may have separated, created a moat of separation right here between the South Massif and the valley floor. If this is the thrust fault, its motion would have been that way, and that would be compatible with creating that moat. And we also found, though, with one of the instruments on board the Lunar Reconnaissance Orbiter, which was a radar instrument, that there was a secondary fault right here. That doesn't show up in the photography. Maybe you can convince yourself it does, but we never noticed it until the radar picked it out. And that subsidiary fault indicates that there was an earlier moonquake, and maybe that's what triggered the older avalanche. Okay. Now, one of the things that makes me think that these scarps, these faults occur as single major jolts of moonquakes is that there's what I call shaken, not stirred terrain around them. And if you map that out, and in fact some dating has been done on the crater count dating that supports this, it looks like it shook the regolith. And so small craters were destroyed by it being shaken. So that's why I call it shaken, not stirred, for you James Bond fans. Well, finally, just a quick mention of this lunar regolith. Here you see it better illustrated by our tracks after the second excursion. That regolith is where the lunar resources are. And if any of you plan to be economic geologists, there's a great future for you on the moon. These resources include not only hydrogen and oxygen and nitrogen and carbon, but you can make water anywhere on the moon, as we discussed a little bit at breakfast. That is important to know. It also, there's helium in that. Solar wind helium, these are solar wind volatiles for the most part, and some of that helium is a light isotope of helium called helium-3. And that's a nearly ideal fuel for fusion power, and that's what my book is all about, is how that resource might be used to not only get us back to the moon, but to supply power here on Earth long term. Well, we had to leave the moon after 75 hours. Cernan tried to get me to go outside and get a really good picture. I, of course, declined. We left the moon with a view of the Earth rise that is, I think, one of the best, although it never made it onto a stamp. And my position is it's time to take another walk on the moon. So with that, if there's time for some questions, I'll be happy to do that. Thank you. Yes? Of weathering?
Weathering.
Yeah, weathering. on the moon is almost entirely due to the micrometeorite impacts. It not only continues the pulverization, but because of the extremely high temperature at the point of impact, it reduces iron oxide to iron. And that's called nanophase iron. We see it in the microscope. And that's what causes the darkening. It's called space weathering darkening of not only the moon, but also of the asteroids.
You mentioned the relatively young age of the ejecta on the crater, correct? On the Shorty crater, you said it was only about 57 million years old?
Oh, yeah, the crater itself, we have done an exposure age of Shorty on the crater, and it appears that it formed about between 15 and 19 million years ago.
Okay. And so, since some of the pyroclastic flows on there are relatively young, No, they exposed the pyroclastic. The impact exposed the pyroclastics are 3.5 billion years old. I see, okay.
No, I probably didn't
So
say.
I guess the question I was going to ask then is how geologically active is the moon still, since there are still some moonquakes?
The thrust faults on the moon are probably the result of the gradual contraction of the moon. It's cooling very slowly, and increasingly it looks like some of them are recent. And in fact, the seismometers that we deployed on the missions have indicated two types of moonquakes. One is near the surface, and there's probably these thrust faults forming. And the energy of some of them is quite high. It's something that probably needs to be considered in the construction of long-term lunar habitats. They need to be earthquake resistant. The other moonquakes, though, are very deep-seated. They're down 1,000 kilometers. The moon's radius is mean radius is 1,734 kilometers. The moonquakes, deep moonquakes, start at about 1,000 kilometers down, and they have the signature of moving liquid, moving magma. And I think the best interpretation of that is that it's iron sulfur liquid that didn't make it to the core, iron nickel sulfur liquid, which would be molten at about 900 degrees C, which is roughly the temperature we think from other measurements that is present down there. And these are responding to tidal forces. They do correlate with earth tides. We're clever people are. Yes?
Dr. Schmitt, in reading the stories of the astronauts who walked on the moon, each of them seemed to say, "We found the best rocks." So as a professional geologist, tell us who actually found the best rocks on the moon. And can you tell us of the 6 missions that landed, who found the oldest rocks?
I think every mission found the best rocks. That's my diplomatic answer. But because we learned so much from each suite of samples. In fact, Neil Armstrong's suite of basalt samples is probably the best suite of those samples that we've ever gotten. And it immediately told us that we were dealing with some very diverse chemistry in the formation of these basalts. A diversity we don't fully understand how it actually occurred yet. But the oldest rock probably is one that I picked up. It was a dunite that at Station 2, I was running by this rock, and this large clast in a breccia sort of jumped out, and I stopped, and it looked, at first I described it, it has a rhyolitic texture. That's another type of basalt, another type of volcanic rock. But then the more I looked at it, I could see quite a greenish cast to it, and it was almost pure olivine. It's what we call a dunite. And now that's becoming an increasingly important sample. Just in the last couple of years, we've realized that its texture suggests that it originally had formed at the base of what has been termed the magma ocean. This was the molten part of the moon formed just after its accretion, and that olivine crystallized and sank to the bottom of this magma ocean, and this rock may well have come from there, based on textures and isotopic analysis. And we're in the process of trying to understand that. How did it get there? It almost suggests that at some point the mantle of the moon overturned, at least locally, and brought that material back up. Yes. Go ahead.
In your book, you claim we're 20 years away from a colony on the moon and 25 from our 5th mission on Mars. How far would you say we're now from those goals, and is anyone actually working towards them?
Well, we're about the same. Hadn't changed. That's based on funding of a business plan, which hasn't happened, and it also and it assumes that it's a private entrepreneurial effort rather than a government effort. Government effort will take longer. Nowadays, it didn't for Apollo, but it would now. No, it's if you could fund and implement that business plan, that's about what it takes. You could accelerate it with some additional money over what I estimated it would take to make it happen. But they're just we have to remember that we have to start over in some respects. Certainly from the human point of view, you need another generation or two of young people to make a return to the moon and on to Mars happen. And that's very important to recognize, that you have to develop a program that attracts young people and gives them a sense of accomplishment in the time that they're going to work it. On the other hand, you can't let an agency get old. NASA has gotten old. So you have to have a way in which you can keep it young, that people can move on after they've done 10 years or so, that they move on into other things. And that's possible. In fact, there's one agency of government, if you want to call it that, that has institutionalized that, and that's the nuclear Navy. The nuclear Navy is always young, and it's because they institutionalize the migration of people as their experience grows and their age grows out into other activities, and then they bring in young people. So the nuclear Navy is always young, and there ought to be some way in which we can get the space agency or a space agency that stays young, since we know it can be done. Now, of course, that's a military organization, and the question is, how do you do that in a civil organization? And I think it could be done.
We wanted to thank everybody for coming, but we were told we sort of got to cut questions off there so that he'll be able to do the book signing at 12:15. So please, everybody stay and get a book and get it signed and meet Dr. Schmitt.
Thank you very much, folks. Appreciate it.